Okay, so moving into 4.4 from 4.3, it's going to make sense. So what we did in 4.3, which is find zeros of polynomial functions, and then use those zeros to then fully factor a polynomial, we're going to keep doing. But the biggest difference is that when we finish, not all of our zeros are going to be these beautiful things like a 1 or a 2 or a 3. And that's going to be the whole point of today's lesson. So it's very much a continuation of 4.3, just adding on. So first things first is that every polynomial function of a degree n, where n is greater than or equal to 1, can be factored into n factors. All that means is that if you have a 5th degree equation, you're going to have 5 factors. Okay, if you have a 6th degree equation, we're going to have 6 factors. And for them to be linear, don't forget that the exponent on the 0, so that what's in here is going to be a 1. So all of these are linear factors because they all have exponents of 1. All right, so first thing we're going to do is the exact opposite of what we did yesterday. Yesterday, we factored polynomials to find zeros, and we're going to start today's lessons with given zeros, go back to what the polynomial function will be. So our job is going to be to rewrite the zeros as factors, and then we're going to write them as a product of linear factors, and then sometimes you'll be asked to then multiply the factors together to give a polynomial function. That'll make more sense when we do this. So the first thing I want to do is I want to change from zeros into factors. So if you notice here, we've got 1, 2, 3, 4 zeros. So we're going to draw 4 brackets. Every bracket is going to get an x minus. So there's 1, there's 2, there's 3, and there's 4. And then you're going to take your zeros and you're going to put them in. So if I have a 0 of -4, this is going to be x minus minus 4. If I have a 0 as 0, it's going to be x minus 0, and then x minus 2, and x minus a third. Okay, that's theoretically done, but we're going to clean it up a bit. 2 things we're going to clean up is that when you're taking away a negative, you're just going to write plus. And when you're taking away 0, you're not actually doing anything. So this is just going to be a factor of x. So we're going to put that out front. So this is going to be x times, now x plus 4, x minus 2, and x minus a third. And that is it for now. So this is expressing my zeros as a product of linear factors. All right, next one. So this one, how many brackets do I need? Well, 1, 2, 3, 4, 5, 6, 7. So there's 7 zeros, so I'm going to have 7 linear factors. Now with this one thing I want you to notice is that when we go to put in our zeros, we've got x minus minus 4. That's the first 0 put as a factor. And there's another minus 4. In other words, this 0 has a multiplicity of 2, which means instead of writing x plus 4 times x plus 4, I can just do x plus 4 all squared. Okay, pause the video and see if you can write the rest of these zeros as a product of linear factors. Okay, hopefully you did pause the video. So then my next one would be x plus 1, again, all squared. And then we'd have x minus 2, x minus 3, and x minus 6. Not too bad, hey? So in other words, what we're doing is we're taking it from having x equals -4 to going back to what the 0 would have been. So if you think of making, like what would make this bracket, x plus 4 equal to 0, it's when x equals -4. So if you think of that from backwards, if we have x equals -4, you could actually isolate, like make it equal to 0 to find what the factor would be. So this is another way of doing it. But ever since I started teaching with like, just draw your brackets, but x minus, people have been less confused. So, you know, you could think of it as the direct opposite of last day, x equals -4, x plus 4 equals 0, that's your factor. Or write x minus and then put all the zeros in, and that'll work as well. And that's it. That is a product of linear factors. So this one, I want an equation of a degree 5, which means I'm going to have 5 linear factors with these zeros. So I'm going to have an x or a 0 of -1 with a multiplicity of 3, a 0 of 4 with a multiplicity of 1, and a 0 of 0 with a multiplicity of 1. So pause the video and write that as a product of linear factors. Okay. So what I would do is put the one with the 0 first, because that's going to be x minus 0. It's just an x. I always write it out front, and then I keep going. So a 0 of -1 means x minus -1. Multiplicity of 3 means I'm going to cube that linear factor. And then my next one is going to be x minus 4, and it has a multiplicity of 1. Done. Sweet. Okay, so now let's amp it up a bit. The next one is that instead of me asking you to express this as a product of linear factors, I'm going to get you to find the polynomial function. And what that means is we want to go a step beyond what we just did. So what we did is expressed as a product of linear factors, and to be a polynomial function, that means I want it as a list of terms in descending orders of power. In other words, you have to multiply it through. And I don't want to multiply through x times x plus 1 cubed times x minus 4. It's just long. And so, I just wanted to make sure you had it first, and now let's do ones that we will actually multiply through. So I won't make the degrees very high on these because there is a lot of multiplying. So here we go. We've got 3 zeros, so I'm going to start off by going p of x equals, and I'm going to have x minus, and x minus. Okay, let's put our zeros in. So we're going to put in negative 5, which is going to make that an x plus 5. We're going to put in a root 3, so it's going to look like minus root 3, and a negative root 3 is going to make that plus root 3. All right, so now to do this as a polynomial function, we have to expand our brackets, which means we're going to multiply through. Looking at this, I hope you see that the first two brackets that you would multiply together are these two, the x minus root 3 and the x plus root 3. If you notice, they're the same bracket with different signs, and when you do this, magic is going to happen. So let's just let the magic happen, and then we'll talk about it. So I'm going to put this as x plus 5, and then I'm going to FOIL these two brackets. So I'm going to distribute. So I'm going to take this x and multiply it by x. I get x squared. I'm going to take the x and multiply it by root 3, so I get root 3x. And then I'm going to take the minus root 3 and multiply it through. I get negative root 3x. And then I get negative root 3 times positive root 3 is negative root 9. And now I'm going to simplify before I start multiplying again. So I'm going to still have this x plus 5. And then this bracket, here's the magic. When you have two brackets that are the same with different signs, they're called conjugates of each other. When you multiply them through, the two middle terms are going to be the same with an opposite sign. In other words, they'll cancel each other out. So what am I left with? Well, I'm left with x squared minus the square root of 9, which is 3. So not only did I get the magic of the middle term going away, but when you times a radical by itself, root 3 times root 3 means that I'm squaring root 3. And squaring is the inverse operation of square rooting, so it just goes away. I'm left with just the 3. So now you can't even tell that this polynomial function would get these irrational zeros. In fact, it's going to look totally normal. So let's multiply the x through. I get x times x squared is x cubed. X times negative 3 is negative 3x. 5 times x squared is 5x squared. And 5 times negative 3 is negative 15. Okay, and then I don't like that it's not in descending orders of power, so I would put it in descending orders of power. So x cubed plus 5x squared minus 3x minus 15. And that would be my polynomial function with a degree of 3 with those given numbers of zeros. By the end of the lesson, I'm going to be giving you this polynomial, and you're going to be finding the zeros. So we're going to be going the way that we did in 4.3. But for now, these are the zeros. They come back to this polynomial function. And again, there's nothing to tell you that these roots are going to be irrational. Okay, so now I want you to try this one. So first, write it as a product of linear factors and then multiply it out. So pause the video, give this one a go. So hopefully you did pause, and we've got p of x equals. So I'm going to have x minus 1 times x minus 3i and x plus 3i. Now, as soon as you see those i's, I should have said this before I told you to pause the video, the only thing that you have to remember from chapter 3 is that if you ever end up with an I squared equals negative 1. Okay, so now, again, you're going to multiply these two brackets first because they are the conjugates of each other. So I'm going to get x minus 1 times, I'm going to multiply through. I get x times x is x squared. X times 3i is plus 3ix. Negative 3i times x is minus 3ix. And then negative 3 times positive 3 is negative 9. I times I is I squared. And then, before I keep multiplying, I'm going to simplify. I'm going to have this x minus 1. And then in this bracket, I'm going to get x squared. My two middle terms cancel each other out. And I'm left with minus 9 times negative 1, right? I squared is negative 1. I should put that here for if you're looking at the notes later. So negative 9 times negative 1 is positive 9. All right, now I can keep going. So I'm going to distribute. I get x times x squared is x cubed. x times 9 is 9x. Now I know there's going to be an x squared term, so I'm just going to do that. Negative 1 times x squared is negative x squared, and negative 1 times 9 is negative 9. Okay, and then that is the polynomial function that has these as its given zeros. Now the next part of this lesson is going to be about why, when we did these, did we always have a 3i and a negative 3i? Why did we always have a root 3 and a negative root 3? Well, it's not an accident, okay? It's on purpose. Whenever you have an irrational zero or a non-real zero or imaginary zero, they will always appear in conjugate pairs, because otherwise they would be part of your polynomial function, and that wouldn't be good. So what we're going to learn is what this word conjugate means fully. So you've got a minus bi. Okay, if you have this complex number, then the conjugate a plus bi will always be there. If you have an irrational zero, a minus c root b, then a plus c root b will always be there. Now, the short story of why this happens is if you look at the quadratic formula, which is how you find zeros, right? Negative b plus or minus the square root of b squared minus 4ac all over 2a. If you look at this, to get a non-real zero or an irrational zero, these don't generally come from, well, they can't come really from factoring, okay? Not nicely. They come from here. So if you think about every time you get a non-real zero or an irrational zero, if you use the quadratic formula to get there, you'd always have two answers. You could get 3 plus 2i, right? But then you'd always have 3 minus 2i, right? It's plus or minus whatever came under the square root sign. And it's that square root sign that gives you the radical, right? The irrational zero, or the negative number, which would give you a non-real zero. So the plus minus is why you always get these in conjugate pairs. It's because of the solving with the quadratic formula or completing the square. But what I want you to notice is that this is your b. This doesn't change sign. 3 plus 2i stays 3, just minus 2i. So if I give you something like negative 2 minus 4i, then the conjugate pair would be negative 2 plus 4i. Do not change the sign on the first term, only on that end, on the thing that's imaginary or a radical. So if you have 1 minus 2 root 3, the conjugate pair would be 1 plus 2 root 3. Okay, try this one. Should have said pause the video. So the conjugate pair of 3 plus root 5 would be 3 minus root 5. Okay, so now what if, for example, the b was 0? Right? What if there was no b term? And so you ended up with just this nice imaginary number that's not complex. It's just a pure imaginary number. Well, it still has to be plus or minus, right? Because even if the b was 0, then you still have plus or minus whatever's underneath the square root sign. So if you have a 4i 0, you will have a negative 4i 0. If you have a negative 7i 0, you will have a positive 7i 0. If you have a root 5, you'll have a negative root 5. And if you have a negative root 3, you'll have a positive root 3. Okay, so this will always happen. So then the next level is the textbook will ask you questions like this. Given that the polynomial function has the given zeros, find the other zeros. Now, I've added on this part, express the answer as a product of linear factors, because I don't want to multiply through every single question. It'll take us forever, so you can practice a bunch of those in the textbook, but I just want to get this new process together, this idea of like these imaginary and these irrational zeros and what they look like and how the conjugate pairs come up. So I have an equation of degree 4. So I know that I'm going to end up with 4 brackets. X minus, x minus, x minus, give yourself more space, and x minus, give yourself more space. You'll see why in a second. Okay, but I know because it's a degree 4, I need 4 zeros. Well, they've only given me 2. And just a heads up, they won't separate zeros with plus or minus signs. It's a comma. So look for the comma so that you can see that there's 2 zeros here. So if I have a 0 of I, I'm missing the conjugate pair of negative I. If I have a 0 of 3 plus root 3, I'm missing the conjugate pair of 3 minus root 3. Okay, does that make sense? So the next thing we're going to do is put these in as our zeros. So if I have a 0 of I can go x minus I. If I have a 0 of minus I, I'm going to go x minus minus I, which means x plus I. And then I put in this whole thing. So from x, I'm going to subtract that whole 0, 3 plus root 3. I'm going to subtract that whole 0, 3 minus root 3. Okay, So that shows me to change my signs on everything after the minus sign. So I would have x minus I, x plus I, and then my other zeros are going to be x minus 3 minus root 3, and x minus 3 plus root 3. And again, you could do this as saying, like, if my 0 is x equals 3 plus root 3, if I isolate and make it equal to 0, everything switches signs. So when they go into the 0, right, when they go in as a linear factor, when the 0 goes in as a linear factor, it changes all the signs. Okay, so some people will put this step, the first one, some people don't, but be careful if you don't, right? Make sure you're changing all the signs. Okay, I would love you to pause the video and now do this equation. Again, degree 4. So how many did they give you? How many are missing? See if you can write it as a product of linear factors. Okay, so hopefully pause the video. We've got p of x. I gotta stop saying that. I feel like a broken record. Okay, so I'm gonna have 4 zeros. I've got x minus, x minus, x minus, and x minus. Okay, I've got an x-intercept, or sorry, a 0 of 0, 3, and negative 2i. That's only 3 of them. I'm missing 1. The only one that needs a conjugate pair is the negative 2i. It's the only one that's imaginary or irrational. These ones, they're integers. They're fine. They can exist on their own. It's only these imaginary or irrational roots that need the conjugate, so plus 2i. So I'd have x minus 0, x minus 3, x minus minus 2i, and x minus 2i. And then to clean that up, as soon as I know I have an x-intercept of 0, I'm not going to put x minus 0, I'm just going to have x. So it's x times x minus 3 times x plus 2i times x minus 2i. Okay, the last thing for the end of this video, and then there's one more video after this, is just all of what we just did, but instead of writing it as a product of linear factors, you're going to write it as a polynomial function. And you'll notice I've chosen a degree 2. So these will sometimes be bigger. You know, they might make you multiply through in the textbook, something like this. It's not unheard of, right? I would do these 2 brackets first, then multiply the answer of that by x minus 3, simplify that, and then multiply the answer of that by x, right? One at a time. But the hard part I find for people here is, what do we do when there's like 2 parts to the 0? How do we multiply through? So we're just going to practice that. So these might get harder, but this is as hard as I'm going to go in the note. So degree 2 means that it's going to be 2 linear factors, x minus something and x minus something. I got to figure out what the something is. Well, they've given me one of the zeros. Okay, and again, no commas. So this is just one of the zeros. So I'm missing the conjugate pair. So it's going to be negative 2 minus 5i. So into the brackets, I'm going to put negative 2 plus 5i. And I'm going to put negative 2 minus 5i. Then I'm going to simplify. So I'm going to simplify by multiplying the negative side through, which just changes the sign of everything in the 0. So I'm going to have x plus 2 minus 5i. And then this bracket will be x plus 2 plus 5i. All right, now here comes the fun part. So this is expressing it as a linear factor. Now I want to multiply it through so I can express it as a polynomial function in descending orders of power. This is just a giant distribution. And so the first thing I'm going to distribute through is the x. I'm going to go x times x is x squared. And then I'm going to go x times 2 is 2x. And then x times 5i is plus 5ix. Now, up to you. You can keep going. So you can multiply the 2 through and keep writing linear, like in a line. But what I like to do now is I've set my stage and I want to match up any like terms as I go. So instead of writing it as a big long line and then trying to find like terms, I'm going to multiply this 2 through. So I get 2 times x, and I'm going to write it underneath the other 2x term, right? These are going to be like terms to collect in the end. Then I'm going to keep going. So 2 times 2 is 4. Well, that's not anything that exists on the top line, so I would just write it on the end. And then I get 2 times 5i. Again, not matching anything here. It doesn't have the x, so I'm going to put plus 10i on the end. Now I'm going to multiply the negative 5i through. Negative 5i times x is negative 5ix. That matches this term, so I'm going to write it underneath. Negative 5ix. Then I'm going to multiply the negative 5i by 2. That's going to match this term. I'm going to have a negative 10i. And then negative 5i times positive 5i is going to give me negative 25i squared, which I'm going to write here because I know it's going to end up as a constant. Okay, now I can collect like terms. Now, hopefully what you noticed is magic happened. You've got x squared. 2x plus 2x is 4x. And here's the magic. 5ix minus 5ix. Yay, the i's go away. The things that make your zeros complicated go away if you do the conjugate pairs correctly. Now we've got 4, take away 25 times negative 1. So I'm actually going to be adding 25. So I'm going to put plus 29. And then I've got 10i minus 10i. Woo! I's are gone. That's it. So good luck practicing this. Honestly, the hard part is the new part I should say is putting the zeros in, right? Getting these linear factors. And then the tedious part is multiplying them through. And just be careful. Go slow, watch your signs, and you'll be fine. So do these mini questions. I assigned a lot because I just find people need some practice with this. But again, as always, do as many as you